here I'm just going to recap what we did this month, and that's essentially went through the mechanisms Mother Nature uses to do transparency and opacity. I went through at least 5 of these mechanisms, and I'm just going to go through them really quick. I'm just going to mention first that quantum mechanics has no explanation for opacity and transparency. Why? Because they use zero-dimensional particles, which ain't particles, and they use waves, which aren't objects. Okay, a wave is a moving vectors. What is a vector? Magnitude and direction. They have all these vectors moving. So they don't have a physical object. They cannot use the term travel through, moving through, go through. They can't do that because you have to identify what object is moving through the substance. And right now we don't have an object proposed by quantum mechanics, okay? Okay, but let's look at what we have. Alignment is one of them. Why alignment? Well, here we did a little experiment, okay? And it goes something like this, okay? We had 2 polarizing lenses, and when we turned it around 90 degrees to the other polarizing lens, the laser disappeared. Okay, it's not on the screen anymore, on the black screen there. And what we're saying is what you see on the left. We're saying when we turn the polarizing lens aside, what we're doing is redirecting the ropes in a different direction.
That's a really cool effect.
Okay, so that's one of the ways I'm saying that Mother Nature does.
I guess you couldn't do that with water when we talked about.
Well, we're getting to that.
Oh, sure.
Give me a second. Yeah.
Okay.
Here's the water alignment. Okay.
Oh, yeah.
And we have we want to know which one is true on the left. Okay. Did the water molecules remain in the same direction with respect to the center of the Earth due to gravity, or did the water molecule stand on its head or on its side? Okay, so that's the question you got to answer in your mind. Again, a question of alignment, but is that why water is transparent? Is it because of alignment, or is it due to something else? So again, I'm giving you the tools to figure out why some materials are transparent, why they're not.
Some hard questions, though.
Yeah, it is.
Noggin scratchers.
Okay, but this is to make people think. Okay, here's quantity. That's the other variable. Okay, and here we have an example. Okay, and here is when we have many of something that is transparent, and now we're going to see when we have only one. So we have a light there, we put a single sheet, and we can see more or less through that sheet. It's more or less transparent or translucent, if you want to use that word. When we put many of the same transparent materials, many sheets, you see that you can barely see the light. So something that is transparent, if we put many of those, it becomes opaque.
Oh yeah, same thing applies to air, right?
If
you look into the distance, the mountain is foggy.
And that could be smog.
It's blurred. Oh yeah, but smog is the same thing, right? It's basically along the same lines.
There are particles in the air, But yeah, that's the issue. The issue is you put many glasses, they turn green and eventually become opaque. So the same glass that you have in your window that you can see through, put 1,000 of them and you can't see through them.
The same thing applies to water, right? If you put your like a ball underwater just a little bit, the ball's basically the same color, but if you keep taking it down, it's gonna start changing. The ball changes color the lower it goes.
And the issue with air is the reason is you would have to put a lot of air, and the reason is because air has approximately the same refractive index as vacuum. Okay, so you would need to put lots and lots of air, maybe so far in the distance that to prove your point that you can't see through lots of air. And
it has to be clean air.
You would say, well, I can't see that far, that's why. Yeah. Okay, and then we have temperature is another variable. Okay, here I made the example where I took a bunch of ice and I let it melt, and you can see that suddenly the pen appears through the water. So what was opaque became transparent simply because of temperature. Okay. Now, one fellow pointed out, says, well, in the case of ice, you're freezing also air in.
Yeah, that's what I was going to say.
Okay, fine, no problem. But see, here's another example. Okay, and this is argon. Okay, and argon, when it's solid or liquid, it's more or less transparent. But when argon is in a gaseous state, it's violet and it's no longer transparent. So it's the other way around in the case of.
That isn't because it's being cooked or ionized?
Yeah, it's true, but I mean, the point here is that here you have the opposite effect. Here you have it transparent when it's in the solid or liquid state, or more or less transparent, translucent, okay? But when you heat it up, okay, or you ionize it, well, then suddenly it's no longer transparent. That's the point I'm trying to make. So all I'm saying is temperature has an effect on translucency or transparency or opacity, okay?
I think the temperature one's more easy to understand.
Well, let's continue because they're related to that. Two things are related to that. I mentioned that the other day, and one is stiffness. Okay, so here we have solid, liquid, and gas, and the issue is that if you have sound travels faster through a solid than through liquid, and through liquid faster than through gas.
Okay, that's a really cool gift. I like
So what you have is sound travels faster. So the question is, why would not something which is solid be more transparent than gas? Because you would think that light has an easier time to travel through something solid than through something that is gaseous. And so the question is, why doesn't light travel through walls? If sound can travel faster through a wall than through a gas. Okay, so that's the issue. And so the question is a question of stiffness, which is related to temperature. Okay, and so here we see a fellow who questions and asks this, or makes this comment. He says, "I think light can be compared to sound." Okay, let's find out. Light is torsional and sound is longitudinal. Yeah. Okay, and the speed of sound is limited by how fast one molecule can transfer its motion to the adjacent molecule. We're talking about molecules, atoms, right? Light obviously is not the vibration of either.
I like transfer its motion. That's a nice way of putting it.
The speed of light is limited by how fast one part of the rope can relay its twisting to the next part, how stiff the rope itself is. And yeah, I made a point of saying that, the speed of light is a constant. I know some people have problems with that because their religion goes down the drain. The speed of light is a constant because, with a rope, very easy to explain, the number of links is inversely proportional to the length of a link. And the fewer links I have, the longer the link becomes. And the more links I have, the shorter the links become. And that's what that equation says. C equals frequency times wavelength. Wavelength and frequency are inversely proportional. And there you see the ropes. You can see 4 links or semi-links, 8 and 16. Okay? And it turns out that this is related to how hot something is as well. Okay? The colder it is, the more we approach, the infrared, and the hotter it is, the more we approach the ultraviolet. Okay, so not only do we have frequency related to temperature, but we're going to find out in a second that there's something else involved. Okay, but here, just continuing with this analogy of sound. Okay, sound is longitudinal. Okay, the particles don't travel from my mouth to your ear. The particle that I'm moving here is not the one that reaches your ear. What's vibrating is the molecules close to your ear, and that's why you can hear. Yeah. So I'm not sending you particles through the air to your ear. What you're hearing is
the motion.
The motion that I vibrate close to your ear.
That's
okay?
weird. I mean, it's always the same gas thing just tapping on my ear. Basically, it's the same molecule.
If you carry it with you, yeah.
If you stood still, it's basically like a telegram.
Yeah, so be aware of that.
That's crazy,
and the question is whether that's the case with a light. Here we have a gentleman. His name was Christian Huygens. Okay, he was a Dutch philosopher, physicist, mathematician, whatever you want to call them. I don't think they were physicists because they did more math than physics. But he's the guy who, in Trait de la Lumière, in 1690, his seminal book, he explained how water waves move. And the question is, is a water wave the same as a light wave? He thought it was at the time. Later on, they discovered the transverse wave. That was Augustin Fresnel. He came up with the transverse wave, which was later mathematized by James Maxwell, okay, a few years later. But the issue is, water waves and sound waves, are those the same thing as light waves? And like this fellow said, one is longitudinal and the other one's not. The other one is so-called transverse. It's not really transverse either, okay, because it's not a standing wave. It's not like you move the rope up and down, okay? It's not like that, which is the way usually it's imitated or simulated. No, what we're talking about is torsion here, which is a little different than moving this up and down, okay? So it's the transverse wave which moves up and down perpendicular to the direction of motion of the wave.
I guess it's confusing to call them all waves.
Yeah. And so I don't think, I'm going to disagree with this gentleman, and I'm going to say that no, I don't think you can relate sound waves to...
because structurally they're different.
Yeah, one relies...
One goes up and down, one is...
Not only goes up and down, but one relies on molecules and atoms. The other one is not really... what you're talking about is a rope. And now we have torsion versus up and down or back and forth in the case of sound, right? In the case of water waves, you have these ripples, which Huygens explained quite well. You have a point source from which a secondary source originates, okay? A secondary wave originates from there. And all these are different waves. Okay, and a standing wave is different than really a torsion.
It's confusing to call them all waves then.
You can call them wave as long as you clarify what kind of wave that is.
Okay, but what do we say? When we say wave, it's different ways of transferring motion. Isn't that what
correct? Yeah, it is. Okay, let's continue here. So we finish
But
up.
by that same notion, the Newton cradle could also be called a wave.
Yeah, it
But
is.
you don't
It's-
really think of it in the term of wave. You're not.
when one hits the other,
Yeah.
there it goes. Okay, so this was frequency, and again, it's got to do with rigidity, and rigidity has to do with temperature. What are we talking about? We're saying that if you have light coming to a wall, the atoms are stiff there because they're all in a lattice, a crystal lattice. That the atoms don't move around as much like as air on the bottom there. And so what happens is it's a shock absorber. And so it continues as a longer wavelength, and that's why it's beyond the visible range. So I'm saying that light is relayed through the cement wall from atom to atom. It doesn't come out the other side as light into your eye. Why? Because it's got a much longer wavelength. Okay. In the case of air, it doesn't do the same effect, and so apparently rigidity has something to do again with why something is opaque or transparent. But
Like if you froze air and made it a wall, it would still be transparent, I'm guessing.
well, again, I showed frozen air the other day, and it's opaque. Okay, it turns bluish. Okay, and here you see another example of this, and that's when you send light, visible light through a prism, it breaks down in different colors. That means the prism, which is a solid object, is somehow serving as a shock absorber. And when it comes out the other side, the wavelengths are longer. In fact, it breaks up into the different wavelengths such a way that you get colors. What is color? Wavelengths.
I like that microwaves and radio waves are light that goes through walls. That's a good way of saying it. They're invisible light.
Okay, and final issue here related to this. We say that quantum can't use particles or waves because what are waves? Waves are a bunch of vectors. All those blue and red arrows that are moving there, those are vectors. What is a vector? It's magnitude and direction. What are we talking about? Numbers. What is a particle? Well, the particle of quantum is not a particle. It's not a corpuscle. What it is a zero-dimensional wave function collapse, if you can understand that. Okay, it's a field that's collapsed because you touched it or looked at it or whatever.
Why do we need that reminder though?
Well, because to show that for what I'm going to say next, and that's this, people think that that waves and particles go through water, and that's not true. Because before you can say travel through, going through, moving through, you got to identify what it is that is traveling, what is moving. And you can't use waves and you can't use particles. So please be creative and tell me what physical object is traveling through, moving through. And you can't say, well, it's light. Well, yeah, you got to tell me what light is made of. And you can't say particles or waves, transverse waves at least. Okay, so that's the issue. The issue is if you're going to use the term travel through, going through, moving through, water, air, glass, no problem. Tell me what it is, what physical object is moving through, okay? Maybe you're talking about a ghost.